Okay, today we're going to start on 8.5 with applications for exponential and log equations. The first one we're going to start with is just interest, just like you would earn interest at a bank. The first one is a simple interest here. I would stand for the amount of interest. The P here is our principal. Rate is interest rate as a decimal, so you will need to change from percent to a decimal. And T is time. Alright, so let's just take a look at just a very simple equation here. So Susan bought a new car for $22,000 at a simple interest rate, paying 6%. So here is our principal. She's paying 6% as a decimal. That is our rate. It's 0.06. And the time is 5 years. So interest is equal to the principal times the interest rate as a decimal times time in years. So that was 5. You put that into a calculator, and she's going to pay $6,600 in interest. What is the total amount she's going to pay for the car? So she's paying $22,000 for the car plus the $6,600 in interest. So that car is going to cost a total of $28,600. If you want to decide what the monthly payment is going to be, we're going to take the total amount over 5 years. That's a total of 60 months, and divide. And we wind up with a monthly payment of $476.67. So all you guys are about to be driving, so that's a really practical application. We also have situations where we have compound interest, and that means interest is not given just once a year, but it's compounding at different time rates. That formula looks like this. Again, P stands for principal. This is just a 1. R is the rate. N is how many times it is being compounded. And then we have NT on top. Again, N is the number of times it's being compounded. And time is time. Annually, if you hear just these words in this problem, would be once. Semi-annually would be twice a year. Quarterly would be 4. Monthly happens 12 times a year. Daily is 365. And continuously, I'm just going to write all for that. If we're continuous here, we do have a different calculation. That interest is going to be the principal times E to the RT if we are compounding continuously. All right, so let's take a look at example number 2. So we have Rudolph invested $1,000 in an account. So here's our principal. The account pays 6.5% yearly interest, so 0.65. How much money will he have in the account after 5 years if it's compounded semi-annually? Okay, so our formula is going to be the principal, which is $1,000 times 1 plus the interest rate of 0.065 over how many times it's being compounded. In this case is twice. It's going to be how many times it's being compounded plus time in years. Again, after that, it's just really calculator work. It winds up being $1,376.89. So over the 5 years, Rudolph is going to gain $376.89. Find the amount of interest. Find the amount if interest is compounded monthly and then compounded continuously. So we're going to just kind of repeat this. We have 1,000. 1 plus 0.065. If we're compounding monthly, that's happening 12 times a year, and 12 times 5. I put that in the calculator. We got 138282. Now you would think compounding monthly, you'd be making a whole lot more money. If you see here, he's only gaining $6 over the 5 years. Let's see what happens now if we start compounding continuously. And again, that equation then changes to A is equal to PERT. A lot of people remember it just by saying PERT. But the principal would be 1,000. E is E. The rate we said was 0.065, and the time was 5 years. Again, in the calculator, 1384.03. So it's really not that big of a difference, less than $10 from the original. All right, let's try another one. Turn your papers over. The Robinsons want to start a college fund for their baby son. They have $20,000 to invest. What interest rate do they need to compound monthly so they will have $100,000 in 18 years? Okay, so this one we're going to fill in a little bit differently. They want to have $100,000. The principal currently is $20,000. That is how much they have to invest. We're looking to find the interest rate, so that's the part that we don't know. We are compounding monthly, so that's happening 12 times a year. And this is going to take place over an 18 time period. So this would be 12 times 18 out here. So the first thing I'm going to do is divide by 20,000. So that's going to get us 5 is equal to 1 plus r over 12. If you multiply these two guys together over here, we get 216. So I need to get to that r there. I need to solve. We got this exponent. So what I'm going to do is just take the log of both sides. Okay. Over here, I'll get a numerical value. It's going to come out to be 0.699. Please round these guys to the thousands just so we keep the numbers kind of accurate. And again, when we are decomposing these logarithms, those exponents can move out front. So I'm going to get 216 the log of 1 plus r over 12. All right, so at this point, we're going to divide by 216. So we're going to continue this over here. And these numbers are getting really small, so you're going to have to bring the decimals out a little bit. It's going to be the log of 1 plus r over 12. So remember, logs are base 10. So I'm now going to move both these sides of the equation into exponents. I'm going to have a base 10 for both of these. What I get over here is 1.007. These guys will cancel out. 1 plus r over 12. I've now gotten the r out of that exponential form. Subtract the 1. Multiply by 12. We get r to be 0.089, which will be about 8.9%. All right, we also need to talk about exponential growth and decay problems. These are your basic formulas here. This a sub 0 will be your initial amount when time is 0. A of t is the amount after t years. K is some constant value of how fast it's growing or decaying. A positive value would indicate growth, a negative would indicate decay. All right, so let's see how we work with some of these guys. Alright, so it says the number n of bacteria present in a culture at time t hours grows according to this formula here. First, they want us to find the number of bacteria at times equal to 0. So it means we're going to put a 0 in for that t. So we're going to have 1,000 e to the 0.01 times 0. So that's going to get us to 1,000. E to the 0. E to the 0 is 1, so that's 1,000 times 1. And we just get 1,000. So that's the number of bacteria at the start time. What is the growth rate of the bacteria? And that growth rate is that K value, and it says 0.01. So as a decimal is this. As a percent, it would be 1%. Then they want to know, okay, so what is the population after 4 hours? So now we're going to put a 4 in for t. So we're going to have 1,000 e to the 0.01 times 4. It's pure calculator work at this time. We wind up with 1,040.81. Then they want to know, when will the number of bacteria reach 1700? So now we're looking for time. So when are we going to get to 1700? All right, so we got to get up into that exponent. So the first thing I'm going to do is divide everything through by 1,000. So I've got 1.7 is equal to the 0.01t. Since that t is in the exponent, I've got a base of e, I'm going to take the natural log of both sides. On the left, we're going to get 0.5306 will be equal to 0.01t. Divide by 0.01, and we get about 53.06 hours. So that's how many hours it will take. Then they want to know, okay, when is that amount of bacteria going to double? So if it's double, you could just put a 2 on this side, because that's what we're looking to see happen. Again, taking the natural log of both sides to cancel out that e, we get 0.6931 equals 0.01t. Divide by 0.01, and this is going to take about 69.31 hours. Okay, the last thing we're just going to talk about for the notes here is half-life. Half-life, if you've learned in your science classes, you may have heard of that before, is how long it takes for something to decrease its mass in half. So just take a look at this problem here. It's telling us the half-life of radioactive carbon-14 is about 5,600 years. If 100 grams of carbon-14 is present in an object now, how much will be present in a century? And then how much will be present in 10,000 years? So the first thing I gotta find is that K value. That's the part that we don't know. I know I want to get to half of the original amount, and I know that the time it takes to get there is 5,600 years. What I don't know is what rate it is decreasing at. So the first thing we gotta do is find out that K. Want to get rid of that e, take the natural log of both sides. So now we've got negative 0.693 is equal to 5,600k. Divide through by the 5,600. Now these numbers are real small. You're going to have to bring the decimals out quite a bit. We have 0.00124. Now I can rewrite the formula. So with that K value in there. So I know I'm starting with 100 grams. It's decaying continuously. So we're into that E formula. I know my K value. We found that out to be negative 0.000124. And we want to know how much will be present in a century. That is 100 years. This is pure calculator work, so we're going to have about 98.77 grams. So in a century, it really hasn't lost too much. And it says, okay, how much is going to be present in 10,000 years? So same formula, negative 0.000124 times 10,000. And again, pure calculator work, we get about 28.94 grams left. And that concludes our lesson on 8.0.